Bonjour. Alors, c'est donc le dernier cours.
So this is our last lecture. We'll keep on speaking about unsupervised learning and recent techniques for unsupervised learning that I find very interesting.
Nous avons parlé la dernière fois de
Last time we spoke about,
l'obstacle, donc mon opinion personnelle qui est
well, my personal opinion that one of the major obstacles for major programs in artificial intelligence is the ability to make machines that can do primitive learning. The main difficulty with primitive learning is that predictions in general have uncertainties. For video learning, for example, many scenarios can take place and they're all plausible. When the future gives information on what will happen, if the machine made a plausible prediction that is not materialized, you must be able not to punish the machine too much for not producing the exact answer. The example I gave is that if you put an unbalanced pen on the tip, it will fall one side or the other. If the machine doesn't predict the right side it will fall, it's not serious, provided that it can predict that the pen will fall. How do you train the machine then? One proposition that I made, well, maybe not a proposition, one idea is to say that the observed output is just a representative of a whole spectrum of future possibilities, represented maybe by a surface or a set or manifold or probability density, something like that. So what you need to do is to have a module in the loss function where you can say that the machine's answer belongs to the right surface, the same surface as the future observation. For that, we can characterize the surface a priori. We need the system, therefore, to train, to learn, to train a part of the model so that it can give us the information if you are on the right surface. I will come back to this a bit. For the time being, well, the last time we stopped with sparse coding, the first topic I'd like to speak about is a powerful idea that hasn't been used much so far, apart from a few applications that I will mention rapidly. I'm referring to the idea of learning inference, using learning to carry out inference. You can reduce inference to minimizing a function subject to certain constraints. Let's take the case of sparse encoding. Sparse encoding, you may recall, is the idea of modeling, let's say, a vector, an image, a patch of an image or something like that, by linear combination of a small number of base functions. You take a matrix, a decoding matrix, you multiply it by a vector and you hope that it will have a small number of non-null components. From there on, you try to rebuild an input. Of course, learning algorithms are required. The way you infer this problem is that you take the input and to find the vector from which you can rebuild the input, you minimize. This is a function of two terms. The first term is a reconstruction, a quadratic loss, the distance between the reconstruction and the input vector, and the second term, which is a convex approximation of the number of components in the explicative vector, which will reconstruct the input. So a vector is Z. There's a minimization algorithm for this type of function, a function with two terms, L1 and L2. There are many propositions about the best way to minimize this function. Lots of open source codes, one called SPANS in particular, by Julian Menrad from INRIA at Grenoble, a very efficient way of minimizing L2. To find the vector, the sparse vector, to reconstruct a particular vector linearly. One of the most used algorithms for inference to calculate the vector z, that is, which is multiplied by a dictionary matrix. This is what we call ISTA, Iterative Shrinkage Thresholding Algorithm. It dates back to quite some time ago. So, optimization methods. I'll skip the details. It's an algorithm like this. You start with a vector z, from which you'd like to reconstruct vector y by multiplying it by a matrix WD. This is a reconstruction. This is the data vector, and it's an error term measuring the error vector between the data to be reconstructed and the reconstruction. This term is a sort of gradient of the reconstruction term, the Euclidean distance between WDZ and Y. Let's say this is just a gradient algorithms for minimizing. But you also have the term L1, which measures the sum of absolute values of the components of Z, which must also be minimized. For that, we apply an iteration that's quite simple. This consists in shrinking all Z components. You put them through a function that looks like this. If 0 is here, it brings together all the negative values to 0 by adding a constant and approximates it by subtracting a constant. The constant here is lambda on L. I won't cover that in detail. Well, the calculation is a sort of gradient step. The difference between these different algorithms depends primarily on how these constants are calculated. Lambda is the constant that multiplies the term L1 in the loss function. If you run this algorithm until convergence, you end up with Z, which minimizes the sum of the quadratic cost of reconstruction. So the square norm of this difference, plus the term L1, which is the sum of the absolute values of the components of Z. This can be viewed as a sort of recurrent network conceptually. Take Y, you multiply by matrix WE, which is defined like this, 1 on LWD. Well, transposed, actually. And then you go through this shrinkage function coming to 0, and you multiply by matrix S defined like this. If you substitute WE and S by their values, you obtain this iteration in this expression. This expression represents this small graph as a block. Y multiplied by WE, shrink, multiplied by S, and you continue this iteration until convergence. This is a sort of recurrent network. There is a subtle idea proposed by my former postdoctoral student, Gregor, who said, why not look at this method, this iterative algorithm, as a recurrent network, and train these two matrices, WE and S, instead of giving them directly the value proposed by these formulae. Why not train them so as to give a quick approximation of the solution to the sparse coding problem? It's like using a recurrent network training algorithm whose structures reproduces the algorithm that you know will give the solution. But recalculating the parameters of this algorithm so that it converges more rapidly towards an approximate solution. For a recurrent network, to train it, you unfold it in time unfolding, as we saw before, and then you train it by backpropagation, provided that this matrix X is the same at all instances. You can do that, unfold it 2, 3, 4, 5 times. If you think that you can do the iteration 3 times, you unfold 3 times, and you train the system to produce the best approximation in 3 iterations of the solution to the sparse code. Oddly enough, it seems magical, but it works very well. If you take the fast iterative shrinkage thresholding algorithms, here the 4 x's represent the fitting over parameterization level, the dimensions of z with respect to y. Z is 4 times greater than y, so you have far more dimensions than necessary. Here, z is the same size as y, so it's far simpler, because there's no competition between the components of z to see which should be activated. Let's take it with 4 times. If we apply the fast ISTA algorithm, in this iteration, this iteration, you obtain an iteration error like this. By training the matrices on the same data, we obtain lower errors, less errors, especially after 1 or 2 iterations even. It seems magical. How is it possible that by learning matrices, you can give an approximate solution, the best one, for a problem faster than with the faster gradient algorithms we know of? The reason intuitively is easy to understand. Maybe theoretically it's more complicated. The reason is that the system is trained to give the solution only for a certain type of data. Here, we're trying to reconstruct parts of an image as well as possible. Image patches are not random vectors, they're very organized, so there may be a mix of W, E, and S matrices that work very well for this type of data, but are not very good for the entire space. So the ISTA algorithm is general and will find a solution regardless of the input vector, whereas this one was trained to give the right solution only for natural image patches. This is how we can obtain a gain, a sort of free lunch, where we obtain approximate solutions faster to an optimization problem than that would normally call for far more time. This type of method, there are several variants of this method that I will not be covering. This type of method, though, is very useful for some type of signal processing, in particular to use sparse coding, but with real-time properties. There's a student of Guillermo Sapello at the University of Minnesota. His name is Pablo Spackman. Use this method to separate sources. For example, a discussion between several people talking together, voices on top of each other, or music with several instruments playing. With this method, you can separate signals that are mixed up quite well. Very quickly in a laptop, it runs impressively. Pablo Scottman is now postdoctorate at my NYU laboratory, and he's still working on some of these methods derived from the same ideas to produce high-resolution images, transforming, for example, a video of natural resolution into a higher resolution image or video. There's another way of using this idea, a similar idea, which is a step towards using or producing networks for recognition, and that could be recurrent too. As we saw in the past, convolutional and feed-forward networks are the best architectures for recognition. There's no recurrence. You often use recurrence when you have sequential data where length is not bounded and you need to recall data far in future. We could imagine, though, that we would like to have recurrent connections in a network that we use at the same time for a feed-forward task. We could take, for example, images, and to recognize them, it's the same architecture as ISTA. You multiply by a matrix that you will learn, and then you put it through a rectification, a ReLU, similar to what we had, and another matrix, and then we add this to the next value. We apply a ReLU once again, and you repeat this module several times, sharing the matrix that corresponds to an unfolded recurrent network. Instead of one layer, it's like having a layer that does the normal processing of a convolutional or feed-forward network, but the layer has a connection to itself through this matrix S, so that it can fine-tune the result. Refine the result. When you think about the architecture of recent convolutional networks that beat records with 150 layers, the 150 layers are all different. But in a way, they may be viewed as a sort of unfolded recurrent network that you unfolded explicitly and is not considered as a recurrent network. That's one good way of seeing things. So here, the recurrent network has advantage of these bypass connections that can directly connect the input to the last iteration in a way. We can train the system then with several loss functions, one saying, I would like this representation to be sparse, so put a L1 criterion, another saying that I would like this representation to be used for classification. I'm sorry, this one. So that would be a matrix, or a few layers in a neural network producing a classification, and maybe another term saying that I would also like this representation to represent all the input information because I want to reconstruct the input. This was done by a former postdoc student, Jose Wolf was his name, or is his name. And oddly enough, it works well. Interesting properties in this system. And the system produces representations of inputs that are sparse representations, a weighted sum of terms in low numbers. Here we have the base functions for reconstructing a given figure using the MNIT database. It's totally connected at each layer. This is the reconstruction progressively of this figure. What happens is that the system starts with a sort of internal prototype of 6, represented a bit by this prototype, which is present in the reconstruction matrix. And then, as you add the components and coefficients that are smaller and smaller, the coefficient becomes the form that was given at the input, and that is to be reconstructed. In terms of classification, it works well. There are lots of ideas to dig into here, where several tasks are done at the same time. One, where you try to classify shapes, a sort of regularization term, one to reconstruct the input shape, and one to produce a sparse representation. I'll come back to this idea of trying to reconstruct while doing classification. To come back to sparse representation, there is one version, one variant that we could write in a convolutional way. Here's the energy function to be minimized with respect to Z for a sparse reconstruction L2, L1, the quadratic reconstruction term again, where reconstruction is a weighted sum by the coefficient Zk of each column of W. So the W columns here are sort of atoms of base functions from which we reconstruct the input function, and L1 a sparse of Z. This is a linear. This is a scalar vector here. We can replace this linear operation by a structured matrix corresponding to a convolution. Each Zk is a map, a feature map. Wk is a convolutional core, reconstructing the input as a weighted sum of the features map multiplied, convoluted by convolutional cores. This is the diagram. We'd like to rebuild the input using the feature map, finding a feature map, so that by doing a convolution of the feature map through cores, kernels, and summing up, we rebuild the input. There were several such proposals dating back to some time ago. When you put this all together in a multi-layered network, you obtain a deconvolutional network, as it is called, a sort of convolutional network where all the hours are reversed from the input to the output, from the output to the input, a sort of generative convolutional network. Here's the advantage and why we want to do this. When we want to use sparse coding on image patches, since image patches are reconstructed individually, don't look at this one, what the system must do is produce base functions that are identical to each other, but in fact they are shifts of the same base function. We obtain things such as, here's a detector of a horizontal edge, another one, another one, another one. All are very similar, but at different locations, because the system must reconstruct a patch for which it is trained. It is not very efficient. It is a bit greedy, because it has to produce several copies of the same base function. Now, if you move on to the convolutional variant, we have a version of a filter with a base function for each position and a large image. The system doesn't need to produce shifted versions of the filter because they're already there. In the convolutional nature of this operation, what happens is that the system can spend its resources on producing filters that are far more diverse. Instead of having shifted versions of the same filter several times, it has more diverse filters. This is what you obtain with convolutional learning. Instead of just having oriented edge detectors, you have detectors of the end of edges, crosses, corners, gratings, and so on. So it's far more diverse. It would be great for this to help with recognition. That's not clear yet, that it helps a lot, but it is used in some cases. Here's another example. When you train using natural image patches or bits of a natural image with convolutional sparse coding, or if you have only, well, here, or you increase the coefficients of the encoder and decoder. If you have only 2 filters, it gives you simple filters. With 4 filters, you start to have oriented filters, bipolar, vertical, horizontal, and here a lot of diversity, even more. Center, surround, with a Mexican hat, oriented edge, and the more you increase the number of filters, the more diversity you have in the filters learned because of this algorithm. To be accurate, this algorithm is not really a sparse encoding, but it's a predictive sparse decomposition done convolutionally. This is a sort of sparse autoencoder, with an encoder taking the input, doing the convolution of the input with several convolutional filters, puts it through a ReLU, nonlinearity, and then you calculate the distance between this and the hidden variable from which you will reconstruct the input. Then there's a second term, which is the reconstruction error. Here's the input and the reconstruction going through convolutional filters, which may be different, but this is what we use for reconstruction. And then we have a sparse term. There's a constraint, since the norm of the columns of this dictionary must be limited within a sphere of radius 1, well, irrespective of the radius, that's arbitrary. So the learning process consists in taking a given point x, you calculate z, minimizing the sum of all these terms. So the term reconstructs the input, but also doesn't deviate too much from what was predicted by the encoder. It's an encoder trying to predict the value of z. This is like what I presented before. You have an encoder that's trying to predict the sparse vector from which you can rebuild the input. This is a simplified version of ISTA that I spoke of before. We find Z minimizing this energy. Once you have the Z, you modify the WK so as to minimize this error, and you change ZK so as to minimize this error via stochastic gradient step. And it's very simple because Z becomes a sort of a target for the encoder. We could use this type of method to pre-train convolutional networks. These methods were a bit successful just before 2012 and the advent of ImageNet, when databases were still very small, or at the time when databases had relatively few classes detecting pedestrians in images. There are just a few thousand examples in a typical database, and the number of categories only 2, pedestrian or non-pedestrian. So using supervised learning with a convolutional network doesn't work very well. But with unsupervised pre-training, it works well. So we have the sparse autoencoder, an encoder, which is a convolutional layer. Here, a rectification. This may be viewed as a ReLU. It's an absolute value, but it could also be a ReLU. We minimize the sum of these terms. So this is a sparse term, and then you take this value to reconstruct the input, and you train this autoencoder here, as I presented before. This pre-trains the filters of a convolutional network, which looks roughly like this. Very generic, not at all task-specific, since we don't use labels for this training. But that gives you a good starting point for a convolutional network. We do that for one layer, and when you're satisfied, you move the decoder, you no longer need it. And you keep convolutional laws that were learned, you still have the ReLU, and then you pool here. This layer may be viewed as containing not only the ReLU but also for pooling. I'll come back to that. Then you connect it to a second layer that you train the same way, totally unsupervised, to reconstruct the input. The advantage is that it forces each layer to maintain the maximum possible information to be able to reconstruct the input from the output. Now we end up with a convolutional network with 2 layers, pre-trained in this case, so that the operation carried out by each layer maintains maximum data so as to reconstruct its input. You can add layers on top and then refine it with conventional backpropagation, giving you, therefore, a starting point. And this works well for things like training pedestrian detection in a large database. In a small database, it won't work well, because all you have to do is use ImageNet for training, and you find it on something else, because it's similar. But in this case, it works rather well. These are the performance of a pedestrian detection system. Precision recall, the number of false positives per image. This corresponds to, I think it's 1 false positive per image. And here, the number of pedestrians missed in the image. A whole system with different architectures, usually not convolutional networks or none of them. And this is a convolutional network trained, purely supervised, and this is a pre-trained, unsupervised convolutional network that refined in a supervised way. So these findings date back to some years ago, in 2011, I believe. Since then, databases have increased in size, and other systems have made progress. But that gives you an idea about the benefits of unsupervised learning, so there may be some hope. Once databases like ImageNet were available, this was no longer used. But it will come back with the arguments I gave you the last time. In practical terms, there are special architectures that are more refined for this, using an encoder, which may be 1 or 2 layers of a convolutional network, a linear decoder, and then sparsity. It's not direct sparsity. on the components of Z, but you pool the components of Z with L2 pooling, a pooling method that we do here. Then you calculate the sum of activations of units after pooling. There's a pooling layer in the system, and L2 pooling in this case.
Et en fait, il y a toute une classe de méthodes.
You have different methods proposed in the past. Why do it this way? It takes some time to explain it in detail, but the reason here is that with two units inside the pool entering this square root, these sums are made on groups, and there are several groups, and you calculate the sum of activations that the groups output. Now, the system wants to minimize the number of groups activated, but within the group you can have as many activated groups as you wish at no cost. Now, the system is organized so that the units that are in a pool are active at the same time, meaning that these are similar filters pooled, grouped together in a pool. Several methods were proposed in the past in different contexts, especially for analyzing independent components and other contexts. But what's interesting about this, and this is more interesting for people in newer sciences than in computer science, is that if you organize these pools, these are components of Z. Here you see the decoder's columns. We're talking about the features extracted by each unit in vector Z. If you group the pools in the pools of packs of units or filters, and if the pools overlap each other, that gives you a sort of topographical map of features that vary continually when you move on the map. It's a theoretical map, left and right, without connecting top and bottom. So we can see a sort of smooth evolution. This is because pools group filters which are activated together and therefore look like each other, resemble each other. If you put groups that are covered by filters that look like each other within the pool, then you end up with this topographic map. If you ask people in neurosciences how neurons are organized in V1, for example, selective for specific orientations, they see this type of organization, something more like this, with singularities and an orientation changing continually when you rotate around the singularity. And you can follow it, the orientations within the system. These are maps produced by an algorithm such as this. An autoencoder, a sparse one, that is not convolutional but with a local connection with overcompleteness. I don't even remember how to say that in French. So these are maps where the colors represent the orientation of the unit's activities, and the same type of map extracted from neuroscience articles measuring the orientation of neurons in the visual cortex. Here's another example of the results with this type of algorithm. So learning algorithms that may be connected to what we know of in what's happening in biology and sparse coding, all of that originally came from neurosciences. It was the sparse encoding. The other methods based on lateral inhibition, more similar to what we see in biology, but it's a bit more obscure. I'll skip this.
Alors, une technique en fait pour...
A technique for trying to learn, well, unsupervised features, that's good, but we like to learn invariant features with respect to certain transformations. This is what we call slow feature analysis. Some years ago, my postgraduate student, Gregor, working on Vista, thought of training a self-encoder to learn not one image but a series of video images, and to say, I will produce 2 features vectors from 3 successive video frames. One that is supposed to represent the content of the frame. Let's imagine that in 3 successive video frames, content won't change much. And another to represent the position of objects in the frame, and that will change as the objects move in the frame. So you take a frame. You have 2 encoders, one to produce the content, and you'll force this one to be the same for all frames successively. And another one encoding object's position. This one can change from one frame to another. But if you do it that way, the system will ignore this part entirely. There's another component. You'll take the result here and put it in a decoder to reconstruct the input frame. So it's an auto-encoder. If you do this, the system will ignore this part of the network and just pass the information directly here. You therefore need to put a constraint on these components so that the amount of information going through L is limited. Sparsity constraints, for example, so that these features here, or these vectors, are sparse with very few non-null components. You will train this like a sparse auto-encoder with constraints on these codes. There's a trick here, though. During reconstruction, you will calculate a term-to-term product of the vector feature obtained through the internal code using a matrix with each of these 2. In other words, reconstructing a frame is the term-to-term product of reconstructing from the object localization multiplied by the object's identity. So this allows you to make the most of a sort of compositionality of the position and nature of an object. Let's say you have the detector of an object shape, and detectors measuring the size of each object. If you activate the one using medium size and the one for a circle by a term-to-term multiplication of these 2 vectors, you obtain a medium-sized circle. This is what would be activated. So you have this idea of a multiplicative unit that is quite interesting. It works quite well. You end up with detectors that detect a specific feature, for example, a horizontal edge without thinking about position. That's for this code here. What we're showing you here are low-level features that activate a unit here that may be viewed as a sort of complex unit after pooling, but there's no pooling. All of these features on the input, irrespective of their position, will activate this specific feature in what we call the what, the content that is. And furthermore, you have detectors, these that say there's something in this corner, but I don't know what. They are detectors, therefore they don't deal with the orientation of the edges, but they deal with where it appears in the visual field. It's a bit hard to see here, but these are filters that localize activity without caring about their nature. We can do both. We can do reconstruction, and it's more or less acceptable. So the idea of temporal learning using temporal consistency is an old idea. You had slow feature analysis proposed by neuroscience researchers in theory, a long-standing idea, but there are many different ways of implementing it. Here's a more recent way. This is a paper released last year with an autoencoder which takes a video frame. It enters an encoder, just a convolution rectification, a criterion L1 for sparsity, and you continue with a linear decoder. You do the same thing then with the same encoder decoder for the next frame. So you can apply this encoding with a reconstruction for each frame. And then there's a spatial pooling, also on features. And you say that you're training all of this in general by saying, after pooling, the representations extracted for these two frames are as similar as possible. So pooling is supposed to evolve slowly in time. Based on after features extraction and pooling, the representation here should evolve slowly in time. These two vectors should be as close as possible. You train them on successive video frames. Typically, you obtain filters like this. These are filters that are part of the same pool. They're supposed to be very similar to each other, just a shift one of the other. Here, too, in groups of 4, they belong to the same pool. So it's quite nice. This is just with a sparse autoencoder. And here we have the typical filters you obtain by training a layer of the same nature. On seed farting, for example, an example of a database. Thanks to this idea, there's a refinement of this trick, which consists in the following. There are two types of data coming out of pooling. First of all, the output of the feeding, which may be a max pooling or L2, a bit invariant to position. If you do a max pooling, there's more information we can get from pooling. The position of the switch that was used, the position of the max, rather, that is propagated towards the output. We can have a sort of separation, therefore, of what and where, meaning the content, that came from the pooling regardless of position. And the position of the switch, which is the max's position, this is the position of the object that we're interested in, but irrespective of its nature. We can try to play predictive games where we say that we'll take 3 video frames and we will try to predict the representation of where and what from the where and whats of 2 frames. You have 2 frames and you predict this for the 3rd frame. And the what or the content of the 3rd frame is assumed to be the average of the previous frames. But the where, the position, will be a linear extrapolation of the positions. We can assume that the images move linearly. From that prediction of what and where, we reconstruct the input using a decoder, and you ensure that you don't move too far from what the encoding of the 3rd frame will produce. It's a bit complicated to implement and to explain. And pooling is a bit complicated, but I will come back to this when giving another example that may be a bit more eloquent. In this case, we obtain as well funny filters, amusing filters, where pools still produce features that are very similar to each other within each pool. Shifted versions, let's say, of each filter. If the pools overlap, this is a linear topology with a sort of overlapping, a slow evolution of the nature of the filters. It would probably work better in 2 dimensions. This can be used to do things such as predicting the reconstruction of frames from. Well, we can train a system like this on images like this containing objects that were turned in all directions, in all positions. And then we can try to do an interpolation of views to reconstruct turned views. These networks are very shallow. If you want to do this at large scale, you need the same idea but with very deep networks. A bit difficult to see, but we can reconstruct views that were never seen based on the posed parameters.
Ok, donc dans la suite, un peu dans la même veine.
Along the same lines of ideas, the same type of ideas, I've been wondering for years about how to integrate supervised and unsupervised learning in a single rule. Algorithms exist for that. The Boltzmann algorithms that are very ineffective, unfortunately, and they're very difficult to scale because that would call for sampling and so on. So it doesn't work very well. This is a joke. It wasn't 1893. It's 1993. Hinton is old enough, but anyway, just to say that this idea is not new. The fact that you must be interested in unsupervised learning, and there's no big difference between supervised and algorithm, but it could be good to have an algorithm that does both in a way, depending on how it is used. The main problem with unsupervised learning, as I said, is that you're a form of supervised learning which is unsupervised by reconstruction. Instead of trying to predict the future in a video sequence, for example, you try to reconstruct the input quite simply. This is what we were trying to do with the autoencoders I spoke of before. An autoencoder is something that finds a representation for the input and then forces the system to reconstruct the image, the input from that representation. As I said before, the system must reconstruct sampling, but not reconstruct samples that were not learned, that are outside of the data density, and that's where the problem lies. This is why Boltzmann machines are very difficult to scale because of the techniques they use to increase the energy of data not observed outside the high-density data surface is extremely ineffective. One method for learning that I've covered before is by reconstruction. You take an input, it goes to an encoder. If it's not very deep, it's quite easy to reconstruct. Let's imagine the encoder is a complete convolutional network, and the output is the object's category. Here, the ImageNet image. Here, a vector with 1,000 scores indicating the likelihood for each class. The problem is that you can't reconstruct the input from this information because this is a function that is surjective. In other words, it associates at the output one output for several inputs. You can shift the objects at the input, but that probably won't change its nature or its output. And therefore, we can't reverse it. We can't start with the class and regenerate the input. That's impossible. There's not enough data. This is why reconstruction learning for shape recognition is incompatible with when it comes to doing supervised and unsupervised. By instinct, classically, here you would say, well, this is not a function, but I can view this as a stochastic probabilistic function. For each label here, there's a certain probability of producing this or that image. So I can see that as a conditional density estimate. And this is the problem with the Boltzmann machines. But this really bothers me. It's very difficult to parameterize the density in high-dimensional spaces like images. So this is a generative model that's not necessarily probabilistic, which is the case for Boltzmann machines. Here's one solution which uses methods I will be presenting, separating in the calculation done by the network two types of data. First, the content, what, and the digital information that you don't want for classifying. Imagine that this is a layer in a convolutional network, one amongst many. You take the input, you put it through convolutions, ReLUs, and you pool. After pooling, you forgot the information on position, of course. So you keep that additional information, and upon reconstruction, of course, there's not enough information in the content to reconstruct. But since you kept the instantiation information on the object's position or on the features, you can do depooling, unpooling, and send it through reconstruction filters to reconstruct the input. Here's not about eliminating information for invariance recognition, but factorizing the explanations of the input based on data representing the content and instantiation parameters such as position or features. Carl Gregor had this idea. Ranzato, one of my former students who was at NYU and now at Facebook, also worked on a similar idea with max pooling, which worked quite well, but it was difficult at the time to do this systematically. So the idea of having units that dynamically choose places in the picture and you keep that information dates back a long time ago. Hinton and Zemel, students too, von der Matterburg in Germany, spoke about similar concepts but far more abstract. Here is how it works. Pooling and unpooling work as follows. You have implementations like this in Torch. For pooling, you take the values that you find in a pool, the values that you wish to aggregate, and you calculate a sort of weighted average of these values corresponding to a soft version of a max. It's not a softmax, but there's a softmax inside. This is what you calculate. You calculate a score between 0 and 1. The sum is 1 for each value, which is just the exponential of the value. Beta is a coefficient that you can choose by hand. You divide by the sum that gives you coefficients between 0 and 1 for each of these values, and you multiply each value by its coefficient. So you obtain a weighted sum of these values, and the weights correspond. Well, the number is higher if the value is great with respect to the others. Where with infinite beta, this term will select only one value, which will be the maximum. So this corresponds to max pooling, quite simply. For infinite beta, it's max pooling. For beta equals minus infinitus min pooling, beta equals 0, that's average. All of these calculations will be equal, so you calculate the average. And you can adjust that continually. But this is a soft version of max pooling, where you can propagate gradients properly. And then you have unpooling. What you can do is take the softmax values here and take this value, multiply it by the 9 softmax values here directly, and reconstruct. But this doesn't work. Too much data is going through the where. If you pool 9 values here, you'll end up with 1 value in what and 9 values summing to 1. So a lot of free parameters in where. All the information is going through where, very little through what, so it can't work. There's too much flexibility in this where. So you reduce this where in spatial pooling to 2 variables, indicating which, well, the average position of activation. It's a bit difficult to understand with maths only. It's easier with your hands, manually. If the maximum value is here, you calculate the softmax of all these values, and then you calculate the value x, y, the coordinates, in fact, that's the average ones. Let's say the expectation of x and y with this softmax, without taking into account the values themselves. And then you use, well, you act as if the entire activity was grouped around this average position. And that's how you do unpooling. Instead of having, if you do spatial pooling, instead of having 9 values here, you would have 2 values only, x and y coordinates. Pooling paints the value that comes from here at the place in the field, in the receptive field, at this location determined by the square. So it's far more compact. The other advantages too, these maps become sparse because there's only one value per block that is written in unpooling. And therefore, you end up with the features map here that is sparse by default. And the encoder is trained to produce features maps that are easily reconstructible. And therefore, they're also sparse by default. A sort of sparse autoencoder without explicit criteria as to sparsity. We can take these small autoencoders with what-where separations and stack them up, giving us an architecture where you have a convolution, ReLU, pooling, you separate where, producing features maps, and so on and so forth. This is a traditional convolutional network. This is a deconvolutional network, the same architecture, but the arrows going in the other direction. And you replace pooling with unpooling. The convolutional kernels are different in one direction or the other. In each layer, you put a cost, L2 or cross entropy, for reconstruction. Here, an actual reconstruction, in the middle, intermediate features reconstituted, and the top classification errors. These systems can be used for supervised or unsupervised learning. Equally, if you have a supervised sample, you put the input, you calculate the output. If you give the desired output, you have a cost that is supervised here. You can do a back propagation and learn. But you can also go back to reconstruction and use this cost as a regularization in a way of the supervised cost. You tell the machine not only you must produce a good classification, but see to it that the features extracted at each layer permit reconstructing the input. Don't lose too much data. That can be interesting to train the machine to recognize categories for which it was not pre-trained. If you have an example without labels, then you take the input, you go through the network here, you copy the output into this, and you go through this network, giving you a sort of deep autoencoder with reconstruction costs at each layer, and you can train it quite simply as an autoencoder. Unsupervised, you don't need labels. It depends on if you know the desired output, in which case you force it to take the right value. If you don't know it, you let it take the value here, and you reconstruct the value as it wishes. That's an example of a static reclassification, reconstruction system that can also be used in supervised or unsupervised learning, where we can see reconstruction as a sort of regularizer, enabling us to use non-labeled samples. This works quite well. Just to show you examples of reconstructions using unpooling instead of upsampling. Many convolutional networks for producing images use upsampling instead of unpooling, just copying values to obtain a high-resolution map, and then you add layers. There are many examples that I've shown you before which do that. But in actual fact, you don't obtain good reconstructions if the input can vary in position, because the system doesn't learn to store positions because it's invariant. But when you do unpooling, as I just described it, you can reconstruct the inputs quite well. Irrespective of this, even with a lot of unpooling, 16 by 16, you can still reconstruct the inputs. This type of technique works quite well on small databases. It's a bit greedy and difficult to implement on large databases like ImageNet. We're trying to do so, but it takes time. But it works on CIFAR, MNIST, and so on with good results. A similar idea is the ladder network, which is a bit similar to this. Architectures, ladder architecture with a forward and backward network, and costs functions or copies without using what-where separations, using other methods, with results that are average for some data and very good on one database in particular, and we don't really understand very well why. This method outperforms everyone on MNIST, but it hasn't been used on other things. We don't know if it works well on SVHN and the like. Good error rates, though, on SVHN. This is a subset of ImageNet with only 10 categories, with few training samples. But you can use a lot of examples that are not labeled. Here it works quite well. Another method that works just as well, but it's very different. This is stacked What-Twir autoencoder with 74% accuracy on this database using the 100,000 examples that were unlabeled. Only 5,000 training samples, but the same convolutional network trained obtains only 57%. So improving performances quite well. Now, let me come back to predictive learning, to be the last topic I'll be covering. So coming back to how to do video predictions or temporal predictions with the problem I spoke of last week. When you have a predictor, if X are frames of a video and you're trying to predict the next frame, or if X is the observation of a pen that's on a tip, and X is the observation of the final state of that pen, or X is the left side of an image and Y the right side, or X is my left profile and Y my right profile, all data inferences that you don't observe because they are in the future or concealed. And the fact that the physical world can be predicted, essentially. So the whole spectrum of possibilities that may take place, like a pen falling in one direction or the other. When you observe the future, the pen falling, you look at this point. But our system predicted another angle. You don't want to punish the system for making the wrong prediction. You want to tell it that it's perfectly correct to make this prediction, because all these points on a sort of likelihood surface or manifold or whatever. I call this a surface. You have observations of the world, but you also have parameters, latent variables that are sort of parameterization of the surface. When you vary Z on this surface, Y bar varies here. That's the idea of latent variable. Sparse coding, for example, does this. Z is a latent variable of the features vector through which you can construct the image linearly. And in sparse coding, this surface is a linear combination of low-dimensional planes. Let's say union of low-dimensional planes in the surrounding space. For other models, it may differ. Imagine you have a whole convolutional network here. You give it an observation. Let's say the previous video frames and nonsense, random numbers encoding the possibilities of predicting. The big question is, how do we design a loss function so that the machine is not punished for this prediction if the future, the data, give you this? You don't know the nature of this surface, so you need, well, one solution consists in learning or training a model to tell us if you're on the surface or not. You'll have two models. The first model producing predictions, and the second model trying to learn the surface. This model will have to observe X's as well. Why do we need predictive models of the world? I spoke about this last week. The reason is that it's only through predictive models of the world that we can plan, that we can predict a sequence of actions to arrive at a given result. Here's a diagram. Imagine that the world is a dynamic system. You have an internal state that you do not observe. It goes to a function, evolutions in the world, producing phi t. You can't observe this. You don't know t. You only observe that from time to time you can measure things on t. Let's say you retrieve an image. This is a partial representation of the internal state of this variable x which is observed. What you can also do is act on the world, giving it an action that will probably influence its future state. But the thing is that you can't observe the entire state. The world may intrinsically be stochastic. But even if you imagine the world is deterministic but not entirely observable, there are many things we can't predict because we do not have a complete vision of the internal state of the world. If I never looked in this direction and I look now, I'll be surprised at what I see. Well, maybe not, because I didn't have the information before. And therefore, we need a predictive model of the world to predict. We have a controller. It is there to take the world to a particular state. The state of the world includes itself, yourself, if you're a robot or whatever. Imagine a dialogue between man and machine. Here's the machine, and here's the person to whom the machine is speaking. The machine makes the person reach a given mental state which corresponds, so the person received the answer. Or through X, the person asks you to book a table in a restaurant. The world must be in the state that corresponds to the table booked and the customer who's happy. Another possible situation is that the world is a game of chess or Go, and you want to take this to a position where you win. The thing is, you don't know how or what the opponent will play. For planning, either you must know the world. That's the case with gaming. You can simulate the game. You can make it run. This is why reinforcement learning algorithms work well on games. On chess, checkers, Go, and the like. Because the world can entirely be simulated very quickly. If the world cannot be quickly simulated, even if it is virtual, let's say StarCraft, a game, or if actions are not discrete but continuous and discrete, that is the case of StarCraft and also of robots, and certainly for a dialogue, then it becomes more complicated. And we need a model of the world. If we cannot observe it, we need a model of the world, which may be viewed as a neural network, which takes the state of the world at time t, saying that the estimate of the state of the world with a bar on top, of course, it tries to predict. Here is a possibility on the future state of the world. It can't be a single prediction because there's a lot of uncertainties, of course. And this state may be observed by the controller, which determines the action to be predicted. The benefits of having this through a neural network is that we can backpropagate the gradients. If I modify my action now, I can ignore the real world and simulate an action sequence based on our forward model of the world, and therefore infer a sequence of actions that will take the simulated world to a given state. And then we can play that against the real world to obtain the results. In cases where the world, well, you have this type of architecture scenario in reinforcement learning. This is what we call actor critical. This is an actor and this is a critic. This critic predicts a value of reinforcement, of a reward, let's say. A more complex situation, this is a sort of complete forward model of the world for planning. This is a standard model in optimum control theory, where you have a model of the system to be controlled, and you can calculate a series of actions that will take the system to a given state. So we have two problems. One, learning a forward model of the world, and teaching a controller that will take the system to the desired state. These are the benefits of training forward models of the world for planning to see what happens when you take a given action or if you do nothing. So this is what intelligence is really all about somehow. The ability to predict is what intelligence is really all about in a way. Here is an experiment. I wasn't a part of this experiment, but my colleagues at Facebook Research did this. Lara, Sam Gross, and Ro Fergus, all three at Facebook. Their paper was just released. They've already produced a system, Sam and Adam, a system which is an interface between Torch and a 3D game engine called Unreal. Unreal Engine, that's it. A 3D game engine which includes physics in a way, where you have gravity, inertia in objects that can collide. And we interfaced, Adam and Sam interfaced Torch with the Unreal Engine so that we can act on the virtual world in Unreal and retrieve an image after simulation step. Here you have 3 tubes stacked up. We connect a convolutional network and we ask it to tell us if this tower will fall. Quite simply, a binary classification. And a bit more complicated, in what position will the cubes be? Let's say at a given moment or at the end. This is a sort of forward model of the physics with respect to this situation. Of course, we can do that easily because we can simulate many situations. Here's an image you give to the system. Here's what actually happens. These are masks of the 2 blocks. And here is what? The forward model predicts a convolutional network predicting an image of a mask quite simply. We can scarcely see the red block below, but the system predicts that this yellow block will fall in this direction. It's a bit blurry, but it's a reasonable prediction. Here too, it predicts more or less accurately. So we can train these on virtual images using different textures and apply real images. These are real images using a video camera. The predictions aren't bad. In fact, it doesn't work perfectly, but it works roughly. Other examples here. Here it got it wrong. Well, not that wrong. Here, it predicted. Well, in actual fact, the tower collapses, but it's a bit ambiguous. You can't see here that this cube was in the back and that it would fall. So the system predicted that it wouldn't fall. But it works in general. It predicts in one direction it will fall, a sort of qualitative physics only based on observations. Accuracy, 89% of the time on synthetic images, a bit less on real images, different architectures. Now, this idea of predictions is very important for video predictions with natural video images. I'd like to come back to this idea of having a trainable loss function that will tell you if you're on the likelihood surface or not. We call this adversarial or generative adversarial networks. By Ian Goodfellow, it dates back to about a year and a half ago. He had this idea as a student in Montreal, Chauvenjo, since he went to Google and then recently at OpenAI a few weeks ago. It's a simple idea. You take a discriminator network that is trained. Think of a convolutional network typically. It will be trained to carry out a binary classification that will tell us if the image at the output is a real image from the database or a fake image generated by a generator. This is our predictor. Let's imagine that you want to do a video prediction. You observe 4 frames and you predict the next frame. but the training set contains the real image. The discriminator will be trained to tell us if the image it receives was generated by this generator or came from the database. So this network is a sort of contrast discrimination function telling you if you're on the likelihood surface or not. We try to train this as quickly as possible, and simultaneously we train the generator, both simultaneously. But theoretical analyses at this stage have shown that the system must learn relatively quickly as compared to this other one. This one is trained to produce predictions on images. The loss function tries to minimize it, that it tries to produce images in the zone that the discriminator considers as being correct, in other words, real. So the data that the generator obtains is a sort of gradient, a backpropagation of the gradient through the network, and the network tells it, if you change the image in that direction, I will think that it is real. So come close to the likelihood surface. This generator retrieves the direction in the likelihood surface and changes its parameters to come closer. This is adversarial learning. It may be viewed as a big loss function where the discriminator tries to discriminate between real and the fake. You can see this as a discrimination of a given loss function, but the generator tries to maximize the same loss function, producing images that are maximally difficult for the discriminator. Conceptually, it may be viewed as an optimization, and this is different with conventional learning. We're not trying to find a point in the space of parameters that's the minimum of a loss function, but the saddle point, the minimum with respect to the discriminator and the maximum with respect to the generator's parameters. So it's a saddle point. It's tough to find a saddle point, even though we know all the parameters we need to maximize and the other we need to minimize. It's a bit complicated and unstable. It's been a year and a half now that people have been playing with this, discovering properties for the discriminator to be able to do its job. There were some experiments on MNIST by Yann Goodfellow, very exciting. Emily Danton, a student doing his PhD at NYU, with Fergus and myself, but I didn't co-author this article, and a series of co-authors from Facebook proposed an image generation system, non-conditional, not for video, just to produce images, using a Laplacian decomposition of images. The way the system generates images is that you have a low-res version of the image that goes into the discriminator coming from the database, and you have a generator, a convolutional network, generating a small image which is sent to a small discriminator. And this is done at many levels. You take the image at a high level, you calculate the difference with this small image, you try to generate the difference between the two images. In fact, you take the low-res image here, you increase its resolution, you'll calculate the difference, and what you obtain is a Laplacian image, as we call it, filtering using a Mexican hat. And a generator that takes the low-resolution image as a conditional input and generates the additional details required to refine this image of a bird. And the discriminator will tell us if it's fake or real. And we do this at many different scales. The generators are not shared, and the discriminators neither. But that could be done. So this is LabGAN for the Laplacian GAN. Generative adversarial network. So you then generate images, you take random numbers, nonces, at the input, and you send them in the system at each layer. You need nonces. So the generator, I forgot to say, takes random numbers at each layer.
en fonction de ça, produit.
and based on that, generates an image different.
Donc là, on lui dit, on l'a entraîné.
So here it was trained on images of towers or churches, I don't know, and it was told to generate here the initial pixels for the low-res image and then refine it, and it generates images that are more or less reasonable. It's not perfect though. Since then, Alec Radford, Metz, and Chintala Radford and Metz are in a startup in Boston with OpenAI. Chintala is a research engineer at Facebook. Very recently, they produced a system that they call DC-GAN, C for convolutional, and they trained this on many databases, especially on bedrooms. These are images of bedrooms generated by their system from a collection of nonces, random numbers. Amazing. These images are quite reasonable. They all have a bed, most have a window, some have cupboards. They're different from all the examples in the learning base, so it's quite extraordinary. The fact that it works, I think, it really is mind-blowing, leading to something that people have been looking for in shape recognition. In other words, parameterization of a likelihood surface that can be very complicated curve with the complicated topology, but it can be parameterized through adversarial learning using random numbers drawn on a hypercube or a Gaussian uniformly, depending on how you generate X's or Z's during learning. This is mind-blowing, showing that there's something deep behind this, and this is a very general purpose technique that should be used for lots of other things. But this may be reduced to the idea of having a trainable loss function, and so on. Well, so they put the code on Torch. It's available on the web. There's several versions that have been implemented. This is someone who trained a DC-GAN on manga characters, and then you can draw random numbers and produce a manga character or a continuous trajectory in this random number space to produce an image each time. So you have a continuous evolution of manga characters changing more or less gradually from one nature to another. Quite amusing. Since space of the random numbers from which we obtain these samples to generate images is flat in a way, a hypercube, well, that's uniform or Gaussian, something like that, a Z number, you can put it as you wish. And therefore, the arithmetic properties are like in work to vec. You can take the picture of a person, an image of a person, find the input vector of the generator that produces this image through a gradient descent. And from that, you can reconstruct the image. You take this vector, you reconstruct the image, man with glasses, you take another vector, reconstructing a man without glasses, then you add the vector corresponding to a woman without glasses, and the result is you have a woman with glasses. And this is quite surprising, because in this abstract space of random numbers, the system discovered a sort of compositionality. Man, woman, glasses, with or without. All these things corresponds to a direction in this space. So this is mind-blowing. I spoke about this in the inaugural lecture. This method can be used for natural video prediction using natural images. Here's what happens when you try to train a predictor to, well, a spatiotemporal convolutional network that takes 4 video frames and puts it in a network that tries to predict the next images. If you train it, minimizing you obtain predictions that are very blurry. Why are they blurry? The best thing the system can do is predict the average of all possibilities observed in the database. And the system very quickly sees that when you have a contour, it can move to one side or the other without knowing in which direction. So it calculates the average, and the result is that the entire image is blurry. One solution is with adversarial learning. Here is a view of this. It also uses this idea of a Laplacian representation of images at many levels for analyzing frames observed as well as for generating the frames. A big convolutional network, in fact. I'll skip the details. Here are the 4 frames observed. Here are the frames in the learning base. Here are the predictions produced by a system trained with the least square method. It's all blurry. This is the first frame and the second one. With a criterion L1, the sum of absolute values of differences between the frame produced and desired, giving blurry results. A bit more robust, but blurry. Here we minimize not errors between different pixels, but the positions of the contours, edges in the image. This is what we call grain difference loss. It still is blurry, and here adversarial learning is no longer blurry. It's quite good. But there are artifacts that we can see quite well, that we can adjust with a bit of GDL, grain difference loss, to avoid this. So it works well. We solved this problem of blurriness due to the fact that you punish the machine for giving the wrong prediction, which is in the right manifold. You insist on making it produce the right thing. It can't. So it produces an average of all the predictions it observes. So it solves this problem, but not entirely. With long-term predictions, of course, after a while it won't. So the problem isn't entirely solved. But clearly, we are making progress, going from this type of prediction to this, which is far more correct. We can see in what direction the balls are moving, and so on. So here are a few other examples. Our 6 frames, the first 4 frames, are surrounded by black. The 2 predicted frames. The 2 predicted ones are to the left. This is with adversarial criterion. The predictions are more or less correct. It becomes flurry after a while, quickly, but after a few frames we can carry out a good prediction. For complete solution, we'd also need to do predictions in the higher level features, spaces, to see that these are characters. This person's in front of this other person. We know that there'll be an occlusion. At a high level, we can see that the young girl will be blown out the candle. So there are many things that we can predict at a higher conceptual level. It would be interesting to do that. Ultimately, the goal would be to have a system that watches a video of, I don't know, an episode of some series, and when the character says the murderer is, the system can predict who is the murderer, who killed him. But anyway, you'll have to do video prediction, but also understand human nature in detective series, and that is complicated, but it also makes this type of series interesting. So there are no limits when it comes to the complexity of predictions. If we can solve it entirely, that will truly be a key and a significant progress in artificial intelligence. So that's it. I spoke longer than expected. As I promised, we will have a Q&A session. Some of you asked questions on the internet. I hope I have a connection. Oh, no, I don't. No internet connection.
Voilà, bon, je vais essayer de passer.
Okay, I'll try to use my mobile phone. Let's see if this works. Yes.
Oui. Non, c'est bon en fait là. Ça marche.
Oh, it's okay. It's working.
C'est pas très rapide. Non, non, mais
It's not very fast, though. Normally, it connects, so.
c'est pas rapide. Hein.
But it's not a fast connection.
Voilà, donc il y a un certain.
Okay, there are some questions that were asked.
Je vais en répondre à quelques-unes.
I'll answer some of them rapidly, and then we'll move on to questions in the auditorium.
L'apprentissage profond et-
Deep learning,
Ouais, alors ça c'est un petit peu
well, this is true. The question is,
une question théorique pour.
are there theoretical uses for deep learning? I spoke about that a bit. Not a lot of theoretical results. There's still a lot of work to be done. But I have high hopes of generating an interest in people who like maths and geometry in particular here through these series of lectures. Because there's still a lot to be done. Lots of things have not yet been understood, especially as regards the geometry of loss functions. I cover that in the seminars and lectures. So this is very interesting to be done, and there are gaps to be filled. A lot of research, but not enough. Stefan Mala spoke about this with respect to convolutional networks.
Preuve formelle, non, j'y crois pas.
Formal proofs? I don't think so. The question is, can we have the equivalent of what... that's your field,
Gérard, pour
Gérard, like what you do for formal verification of programs. In learning, it's hard to do. They're trained, so how can you prove that it works properly in a situation whereas you have to explore all possibilities? That's not really possible. It's no more possible than to do that with a person, to see if someone is completely trained for a task. You have to test out the system as much as you can in systems that are not dangerous. It takes years to train, several years to train a pilot of a plane, and a lot of experience for him to get out of trouble. So it's all about training reliable systems, and the problem has not been entirely solved yet.
Alors les histoires d'entraîner sur des empiriques, donc
Training,
classique pour
a conventional method for training networks, I spoke about that, on restricted databases with few examples. It's all about pre-training a network on a similar database where the native inputs are similar even though the tasks are different. And then you adjust,
réentraîner.
you retrain with the database you wish. It works well. A good demonstration of that in a Facebook system. I don't know if I have a video on that. I don't think so. No videos on that, unfortunately. But you can find it everywhere on Facebook.
Un groupe
It's a group, a Facebook group, in charge of building
système de communication pour donner accès
communication systems to give internet access to developing countries with little telecommunication infrastructures. Facebook is suggesting building huge planes the size of a 737,
solaire, donc ils peuvent
solar powered. They can stay in the age for several months,
donne l'accès à l'internet.
giving an internet access directly to an entire zone by flying over the zone. These people came to see us and they said,
Est-ce que vous auriez une méthode qui permettrait
do you know how we can analyze satellite images to try to estimate population density everywhere around the world so that we can optimize the position of these self-driving planes. So, okay, here's the code for a convolutional network. If you have the database, it can work. They used an internal Facebook service with a pre-trained convolutional network. It's like ImageNet, but bigger, for recognizing natural images. In-house, Facebook has a service where a group can take pre-trained convolutional networks and just train the last layer on their data, or the two last layers. So all the features and all the previous layers are already trained. So it doesn't take a lot of data to train the last layers. So they took a network and they trained the last layer to estimate the population density for a satellite image. And then they applied that to the world at large. And now we have a world map of population density around the world that will be made available by Facebook during summer. Very useful data for the rest of the world, and not just for drones, but for lots of things, for infrastructures, culture, to detect population movements around the world, migrations, and so on. And it's very simple to implement.
Okay, qu'est-ce que je pense de...
What do I think about quantum deep learning? Well, quantum computing to begin with. I hear this question a lot because there are lots of speculations that quantum computing can help to solve learning problems. The best example we have is that machines that are close to, or the closest, let's say, to being used in actual fact, a deep wave computers that can be used to minimize particular functions. If they have a lot of local minima, they can use the notions of the tunnel effect in quantum computing to go from one attractor to another, crossing potential barriers that accelerates the minimization of complicated functions. But I'm skeptical because these machines are very expensive and not very flexible, with major limitations. So programming the functions we want for learning is a bit complicated, and it's very difficult to rival with the progress made by mainstream technologies in terms of GPU and the like, with so much money invested, huge amounts. So there may be more in the future, but for the time being, I don't see where it's going. We've heard a lot that Google is interested. There's one person who's interested and who bought a machine. But it's not a major effort for Google. They will explore, but probably not invest a lot. I have my doubts. We may have theoretical results in the near future that can show that quantum computing allows us to do the nearest neighbor calculations much faster than conventional computers. But I won't hold my breath in the meantime. What cannot be done with deep learning? We spoke a lot about that. There are lots of things we can't do. Common sense, unsupervised learning, which must be enhanced. We haven't solved all the problems. So that's what keeps me busy for the time being. Distributed learning. Okay, this is a technical question. What is the best way to distribute calculations on different machines in mini batches? How do you distribute that? There are two main ways. I spoke about this a bit. One, parallelization by synchronous gradients, where you simply divide the mini batch into as many portions as the number of GPU boards, and you calculate the gradients separately on those portions of the mini-batch. You average out the gradients, and then you update the common weight vector and you redistribute. That's a synchronous gradient method. Asynchronous methods don't work well, with each GPU working at its own speed, and from time to time it sends its gradient which overwrites. A method was just proposed by Google, where you're synchronous, but not waiting for all the GPUs. GPUs are on several machines, Sometimes they work at different speeds, you have collisions of the network, so you wait for 95% of answers and you stop there. Those who are late are ignored. And that seems to work well. You also have elastic techniques that I spoke of some time ago, where machines work independently of each other and they're connected by elastics or springs, since the value of my parameter must not be too far afield from the average parameters of all the GPUs. This is still being explored. A lot of research and the performance of all these algorithms largely depends on the underlying performance of the communication material, and also significant progress is being made there. But also the software infrastructure. We need low-level communication protocols that are fast, and for the time being, we're using high-level libraries containing a lot of data. By the way, Google just came out with a parallelized distributed version of TensorFlow, which wasn't available before. They just released it yesterday, I believe, which is a detail, but it's a possibility. A question that we can't see. Oh, yes. Here's a question that's quite interesting for those who like public relations. Would there be any demonstration of unsupervised learning that would have a similar media impact, that would strike people's minds, like Deep Blue AlphaGo? Well, gaming context, that's a bit artificial. All methods can't necessarily be transposed to real-life methods. That's like Watson with EBM. The question is there something equivalent, a task that we could prove to show the success of unsupervised learning? I'm open to any suggestion. I would love a task like that, so that we could focus efforts on an interesting problem. One specific problem with unsupervised learning is that it's not clear how to measure its performance. The criteria are not clear. We look at the images generated by a bedroom generator. They all look pretty, but how can we objectively measure the system's performance? That's not clear. We just don't know how to do it yet. False proposals were made, and I will eliminate them straight away. People who say it's not complicated, you calculate a likelihood of density, the likelihood of data, test data given by your system. It can't work. The systems are not necessarily probabilistic. They don't necessarily produce probabilistic solutions. The best way to produce a maximum likelihood for discrete data is to have zero everywhere else. So it's not a good criterion. It's not an objective criterion. This is an odd question. Why not use optimization methods with particle swarm? These are optimization methods with black boxes where they do not assume that you know the function's gradient. You know the optimized function, you can't calculate its gradient, which may be obscure, so you throw in a particle swarm measuring the function's value at several places, and then you can try to estimate the function's form from the values estimated by all the particles, and then you move the particles so as to come closer to a minimum. The reason is simple. It's far, far less efficient than gradient descent. The gradient data gives you, after all, an idea about the direction to go in to minimize the function. And it's not faster, and it won't converge. Okay. I won't spend too much time on this, on all these questions, because I think we have a lot of questions, and I would like to have a Q&A session in the auditorium. One question pertaining to what Jeffington called dark knowledge.
Alors, je me rappelle plus quelle était la question.
I can't remember the question, but I think it was amongst the last questions.
On va pas la trouver là, mais
I can't find it here. But anyway, dark knowledge was proposed by Jeffington. The idea is that you train a network that may be quite large. What you'd like to do sometimes to optimize its use is to train another smaller network to calculate the same functions. It sounds silly. Why not train the small network directly on the database? But the small network may very well have problems with finding the right minimum. This is an odd phenomenon that is not fully understood, whereby you train a large network and then instead, well, you send in training samples, labeled or unlabeled, maybe in large numbers, and each time the large network generates an output configuration which you use, whatever it is, as a target to train the small network. It imposing a lot of functions, the type of functions that the small network can learn. It must learn or read a giraffe but produce the same score as a large network, setting more constraints for the system so it learns better and is less over-parameterized. That makes it possible, let's say, to produce small networks emulating a larger network that was trained elsewhere. This is something that you should know. It works quite well for compressing networks and so on. Anyway, one question.